right? We have to reach a contradiction in every case. And in this case, we have not reached a contradiction in the loop case. So we know that we're in trouble. And now whenever this happens, some part of your brain should think, maybe it's recognizable, right? Because like the fact that it didn't work out means that you might want to think about whether it's actually recognizable. Now, luckily for us, he already thought about that. And he was like, I don't see it, man. I don't see how we're going to do it, right? Like, we could try to do some triangle scheduling, but what are we going to do if we accept some string? We don't know if that's the only string, right? So usually I would be like, okay, let's think about recognizability, but you've already thought about it. You get your token for that. And now we should get back to this proof, right? And see, can we repair it somehow? Can we actually find some way of getting a contradiction? Yeah, do you want to give me your idea? Question. Yeah, sorry.
I guess I'm confused why the language is like only the empty set. Like, wouldn't it also loop if the language had size of one? Because like.
Okay, good. So let me just pause you for a second there, right? So we have built the machine so far, right? We haven't talked about what happens below the line, but it doesn't matter. If our loops, this is basically the entire machine, M, right? And everything that's happened so far didn't even depend on the input x. So no matter what the input x was to the machine, M of x will just loop. Do you agree? So that means it just doesn't accept anything. Yeah, that's cool. Yes? Okay. With what? Right, okay, so your idea is let's try to run it in parallel with something. But what? Like if you run it in parallel with M, that's just like some weird recursion, right? Like it doesn't actually do anything, right? So it's a little unclear what we would be running it in parallel with. Do you agree? Yeah? Sorry, can you say it a little bit louder? I can't hear you. Run it in parallel with like the recognizer empty, but okay. So the recognizer for, okay, you're totally right that there was a recognizer, right? For non-empty, right? But that recognizer took as input a Turing machine, right? And like that's the thing that it tried to do the triangle scheduling on. So if we tried to do it in parallel with that triangle scheduling, what would be the machine that we're running it in parallel with, right? Does that make sense? I still like these ideas. Like it's good. I'm glad that you're actually thinking about it. It's just not clear what we're going to do it with, right? Like if we try to do it with some triangle scheduling, if you ran it on M, we already know it's just going to loop everywhere. So that's also going to just loop, right? And I also want to just like bring us back to just think about what the problem is, right? The problem is that we need to reach a contradiction, right? For the contradiction, we need that M actually belongs to singleton, right? Right? Like when our loops, we need it to be the case that our machine actually belongs to the singleton language, right? So we need to think about something else to do, yeah?
So we want to ensure that we have one string that's accepted if our would loop.
Yeah.
So what that is, just say like if x equals 0,
yeah.
like then
Just accept. All right, great. Let me just say his idea for everyone, right? So the idea is like, why don't we maybe not run R yet, right? Let's actually have a instruction first that just says if x equals, what's your favorite string? 0, okay. If x equals 0, right, then accept. Right? So if the string is actually 0, then we're just going to stop and accept right away, right? And then let's run R on our own description, right? And yeah, that works. That solves the problem, right? Because let's analyze it. Now, if R loops, then L of M is just 0, right? Which is, and that implies, of course, that M is in singleton, which is indeed a contradiction, right? R is only allowed to loop when M is not in singleton, right? Awesome. Very nice idea. Totally worth the token, right? Do you guys see that? That worked out, right? Of course, we still have to finish the proof. We haven't handled the accept and reject cases yet, right? So let's do that. Someone want to help me finish this thing off? Yeah? Okay. If R accepts, and again, let's just think about that before we write it. If R accepts, that means that R, again, thinks that M is in singleton, right? And now we have to watch out because we did already accept 1, 0, right? So what do you suggest we do here?
then let's just accept it.
Okay. So you're saying let's just accept one more string. Then accept if and only if. What's your favorite string? 1. Okay. Right? So we add that and otherwise reject. And if we do that, then we have the case if R accepts, then the language of our machine is 0, 1, right? Which implies that M is not in singleton, which is indeed a contradiction, right? So that works right away. Excellent, totally worth a token. Note that we actually had a lot of freedom here, right? We could have just accepted everything, in which case it would have been, L of M would have been sigma star, which is also a contradiction. But, you wanted to be careful with how many things you accept, which is cool. And that works. And did you want to keep going? What if R rejects? Mm-hmm.
And we already have like the one string x equals 0. So we'll just reject.
Just reject everything. Yeah. Right? And again, what does that mean? That means if R rejects, then the language of M is indeed just 0, which implies M is in singleton, which is just the same contradiction that we had in the loop case, right? And that works. That's the end of the proof, end of the analysis. And we have unrecognizability. Yes?
Why do you say accept if and only if x? Well, it would also is it also fine if you just say accept if x is 1? Is there any difference? Why do you add?
If and only if. I just wanted to be clear that's what his suggestion was, that like we only accept one, we don't accept anything else. So just to be complete, I actually kind of overwrote it. I said if and only if x equals 1, otherwise reject, right? Which is kind of implicit, but just wrote it out. Just to be super careful, just to make sure that you can't misinterpret what's written here, which is something I highly recommend you guys always do whenever you're writing up solutions, just so that there's no possibility of a misunderstanding, right? Does that make sense? Okay. Any other questions about it? Does it make sense to everybody? Yeah. Cool, right? So singleton just works out in this way. I want to point out that if we think of like non-singleton, this is the set of machines such that L of M either has size 0 or L of M has size greater than or equal to 2, right? Your same intuition applies, right? Like, how are we going to check this? Like, how are we going to recognize this? It seems pretty hard to do. And I actually want to just point out, in this case, it's even easier, right? So, okay, let me just write it. Obviously, we're going to have the suppose not, all that stuff. We start building M of x. And we, of course, let alpha equal our own description. And now, if we just run the recognizer directly on our input, we're already fine, right? We've already got a contradiction. Because if this loops, the language is empty, which means it is actually in non-singleton, which is a contradiction, right? So I'm not even going to bother to write the remainder of it. It just works, right? And this is a good exercise for you guys to fill out later. If you have any questions or worries, then please raise your hand. But it turns out that non-singleton is actually really easy to prove is unrecognizable. And so we actually have an answer to your question in the back there, right? That in fact, both L and L bar can actually be unrecognizable, right? And in fact, this is the much more common case. So much more commonly, languages and their complement will end up being unrecognizable. It's just that one of them will have a really easy proof, and one of them might have a little more complicated proof. Actually, sorry, one of them will definitely have a little bit more complicated proof, right? Because the looping case can't be a contradiction for both L and L bar, right? Any questions about this? Cool, right? So again, like one of the points that you guys should feel from this is like undecidability, straightforward. Unrecognizability, you actually have to like think and like play with it, and there's like more, let's say, creativity that is required sometimes, right? To like figure out how you're going to get the contradiction in the loop case, right? Yes.
Could you go over the proof of the singleton, just like one more time?
Sure. Yeah. So this is the construction, and this is the proof, right? So, and the key idea, right? Like the key thing that made it work was this step, right? That when we built our machine, no matter what, even before it even tried to run the recognizer, it just accepted 0, right? And what that did was ensure that there's always at least one string in our language, right? And that just kind of set us up to be able to get a contradiction in all the cases. So then we thought, all right, let's go ahead and run the recognizer. The first possibility is that R could just loop, right? And if R loops, then we'll never make it past this point, right? But R will loop no matter what the input is. We've already accepted 0. Everything else will be not in the language, right? Because it won't be accepted. So then the language of the machine will be just 0. You agree with that? And that's a singleton, right? So M is a singleton, which is a contradiction, right? Because you're only allowed to loop when something is not in the language, right? So we get our contradiction here. The other cases are even simpler. So if R accepts, that means it's supposed to be in the language. But in that case, we'll just accept some other string, in this case 1, in which case the language of the machine is 0, 1. That's not a singleton, right? So that's a contradiction, right? Because again, you're only allowed to accept when M is in the language. So R is saying, hey, you only accept one string, right? If we go back to like that rebellious teenager thing, right? So like our recognizer, parental figure, is like telling you, you will only accept one thing, right? And then we're like, no, I refuse to listen to you. I'm going to accept one more thing than the person I already accepted, right? Than the string I already accepted. And that's our way of getting the contradiction, right? Similarly, if R rejects, again, like R is telling you, you will definitely not only accept one thing, right? In that case, we just reject all of the other x's, and L of M will be just 0 again, in which case you'll be a singleton. So again, you will be not doing what R said you would do, right? So in all the cases, we get a contradiction. Yes?
Sorry, I feel like I'm almost there, but
Yeah?
I don't quite understand. Can you explain the part of if R loops, then it's a singleton? I don't understand this part.
Okay, yeah. So again, if R loops, we'll never make it past this dashed line. You agree? Because we'll just be running R and it'll just be looping, right? And in that case, well, we already accepted if x was 0, right? So we know that the language of M at least contains 0. You agree with that?
I don't understand that part. Why does it at least contain 0 if it loops? Because if it loops,
Well, hold on. Good. I'm glad you're asking me that question, right? If the input x was 0, then we actually never even make it past the boxed thing, right? We already accepted, right?
yeah, so it wouldn't loop. It would just accept.
Yeah, right? So like we don't even have to worry about that. That's why 0 is definitely in the language, right? It's only if the input is not 0 that we bother to run the recognizer, right? And if it's looping, we're definitely not accepting anything else, right? Like M will just be looping. It will never get to an accepting state, right? So in that case, the only string that was accepted by our machine was 0.
Oh, I feel like the part that was confusing me was that because I didn't understand what if there's no 0 in the language, but now I understand because we just made it that way that we just accept the 0. So it
Yes.
doesn't matter what. Oh, okay.
Yes, right? Because we have to think, how will this machine behave for all the possible strings that could be input, right? And we observe that if the input was 0, then we would definitely accept. So 0 is definitely in the language. But for all of the other strings, we would just be looping at this point.
And like if R doesn't accept the 0, then that means that there would also be something else.
Well, once again, R is not the one accepting 0. It's M, right? The M, the thing that we're building. Yeah. But I think you just misspoke. That's fine. So like if M will accept 0, but for everything else, we'll run R of alpha, right? R of ourselves. And that is the thing that'll be looping.
And why did you write 0 comma 1? Is 1 just like a random?
Sorry. Here, so first of all, this case is all done now, right? Okay. So on the other hand, if R actually accepts, then what your friend behind you suggested is that we're also going to accept 1. So if we also accept 1, then the language would be 0 and 1. Right? Okay. Yeah, it takes some time, but just it's good to just let it seep in. Did you have a question or?
Yeah.
You can,
Like I 100% get it, and I get why it leads to contradictions.
Mhm.
The only thing is that like I'm just kind of a little stuck on like putting if x, then except like in all the other times we've just said accept or reject, and I'm assuming that's like all the x's. So if the point is for L of M to contain 0, why are we saying if x equals 0? Why can't we just like aren't we supposed to assign zero instead of like asking if it is zero?
No, like even think back to like DFAs, right? Like there's always an input to the machine, right? That input is the thing we name X. So in order for our machine to accept 0, you have to look at the input and see, is it 0, right? And that's like if X equals 0, then accept.
So why are we only running it on like one input as opposed to like any of the other inputs that could be in there?
We are analyzing it on all the possible inputs. But the way that we decided to make the machine, it only accepts if the input is 0, right? Like we did this on purpose. We were like, I only have to think about the input 0. All of the other inputs will lead us to running the recognizer. Does that answer your question?
Yeah.
Okay. All right. Yes?
Are there no interesting languages that are unrecognizable or undecidable that don't involve machines as in terms of like the definition of the language?
There are so many of them. And some years I get to give a lecture on it. Unfortunately, this year we have run out of time. But it requires its own full lecture to think about. But yeah, they're actually really, really beautiful and interesting languages that don't seem to be about Turing machines, but in fact they are. Like that's the reality of it. And I gave the example we didn't talk about how to prove it, like of Minecraft, right? Like Minecraft doesn't seem to be about Turing machines, but in fact you can build a Turing machine in Minecraft, right?
They're like unrecognizable and undecidable.
Unrecognizable. Yeah, yeah. Minecraft is actually also unrecognizable.
Oh, yeah, you mentioned that earlier.
Yeah, yeah. You just have to make it the opposite. Just like this torch will never appear.
But in that case,
Right.
that is a Turing machine still. So it's like
Exactly.
still like
Yeah, yeah, yeah. So
that
that's what's so interesting is that all of the examples that we know of unrecognizable or undecidable languages, even the ones that don't seem to be about Turing machines, they're actually about Turing machines.
Okay, see, that was my question.
Yeah, 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 yeah. For example, do you guys know what a Diophantine equation is? Diophantine equation? Basically, write like a polynomial equation. Like you have a bunch of variables, some polynomial of them, and you're asking, is there an integer solution? Right? Does not seem like it's about Turing machines at all. Right? There are only a finite number of variables. The variables now can take any integer solution, so there is some infinities there. And all you're asking is there an integer solution? It turns out there's a crazy way of like taking a Turing machine and converting it into an equation such that it will be solvable if and only if the original Turing machine halts. Which is nuts. Like it's actually crazy that's possible, but it is. Yeah.
So for like languages that aren't directly related to Turing machines, how
Mhm.
would you like prove their offset to say primes, right?
Yeah, yeah. Okay, okay. So okay. Let me be clear. That will require at least one full lecture, which we do not have. So I will not be explaining that except maybe in office hours.
The language
Um,
prime was given as a practice problem in our discussion. So is that going to be on the exam?
so wait. Primes is completely decidable,
Oh, yeah. Okay.
right? I mean, you guys all know how to do it. Like you guys all know how to decide the language primes, right? You just like try to divide it by everything that's smaller than it, and if it doesn't get divided nicely, then you know it's prime, right? So you guys learned that back in like middle school or something like that, I imagine, right? Yes.
So I definitely got the analysis part of it, and let me know if this question is like taking too long and I can just ask an office hours. But I definitely understand the analysis, but I feel like the setup that the friend suggested
Mhm.
is still quite unclear with the below the dotted line. If R accepts and if R rejects, because right there and on the left we were talking about like if R accepts then accept, and if the opposite R accepts then reject. But here it's like a different concept, and I feel like I just don't quite understand what's here. But I understand like if that is this, then why that is. But I just
Okay, okay. You know what? I think this is one of those things you're gonna have to stare at for a little while, and eventually it'll make sense. And we can talk about it in office hours. I think it'll be good if we move on. I do want to give you guys at least a few other examples, or at least 2, let's say. We have an hour, so I think hopefully we can do 2 more. Okay? I just want to equip you guys with like good tools, right? So if it is okay with you guys, let me again just suggest a language. So it's a really nice language. Kind of in the same theme of like Singleton. And this time, sorry, let me use my color scheme. So let's define infinite. So these are just Turing machine descriptions such that the size of the language is infinity. Okay? So the machine accepts an infinite number of strings. Okay? And again, we're going to try to prove that it is unrecognizable in the usual way. So, suppose not. There exists a recognizer. And we're building our machine M of X. We'll get our own description as usual. But now what? Now what? Yes? Okay. So hold on. So, yep, we should always start with the most straightforward idea, right? So let's just go ahead and run the recognizer on our own description, right? And as I said before, for recognizability, the first thing you ever want to think about is the looping case, right? So let's think about that, and again, I want you guys to think about it. So, what happens? Like, what if R of alpha loops? Yeah. So in that case, the language of the machine is the empty set, which is just not a contradiction, right? The empty set is not an infinite language, right? And again, like, what just happened, right? We asked the recognizer, what do you think I'm going to do, right? And the recognizer, by looping, says, I do not think you're infinite, okay? I do not think you accept an infinite number of strings. And we were like, yeah, okay, fine, I want to accept anything, right? So like, we just agreed with the recognizer, right? So yeah, that does not work, right? So we definitely need to mix it up. We definitely need to think about some new ideas here as to how we're going to attack this, okay? And let me, again, just briefly say, I love it. I see lots of hands in the air. I definitely want to get to you guys, but just briefly I want to say, just doing this won't work, right? All this does is accept like one string, right? And we actually need, in the case where R loops, we need to accept an infinite number of strings, right? So this is definitely going to be a little more challenging. And let me just call on something I haven't called on at all today. Yeah.
Could we, like, I feel like proving an infinite is hard. Could we go with the infinite bar where, because in, like, earlier we had that.
Okay. You're trying to think if we could use that earlier idea. Yeah. So I'm just gonna let you know that is not gonna work out. So yeah. In fact, the reason why I went to infinite is that finite is actually really easy to prove that it's unrecognizable. And in fact, it's just because this is a contradiction in that case, right? So yeah, this is going to be another example of a language where both L and L bar are actually unrecognizable. I'm just jumping straight to the hard case because I want to make sure that you guys see it before the final. So, yes? Yeah. Yeah.
So intuitively we want it to have accept all strings with loops. So let's say we
Somehow.
have like enumeration of all strings.
Okay.
We run like one step of R,
Okay.
and then accept like x1, then accept x2. So then if R keeps on running, then eventually you'll be accepting every single string.
Okay, I like it. I like it. That's a really cool idea. Let me just say it again for everyone, right? To see. So basically, you are again trying to do some sort of parallel thing, right? And maybe we can write it this way. So you want to build a kind of funny machine, right? That sort of counts out the strings. And if the input is that string, then it accepts, right? So let's just like give that a name. So you're saying let the Turing machine n be n of x will just have for I in sigma star, right? You'll just like enumerate all the strings in some like standard way, right? If x equals I, accept. That's what you said, right? That basically you're just gonna like keep, like eventually you'll accept everything, but you do it like slowly on purpose, right? You actually like count out all the strings, and when you finally reach the input string, that's when you accept. Yeah? That was your idea, right? I just want to make sure I'm being faithful to your idea. Yes, right? And then your idea is let's run R of x and n of x in parallel. Right? And then we'll need more space to write the rest of it, but that's okay. Let me erase this thing. Very cool, right? Really, really interesting idea. Totally worth a token. Let's think about it. Let's think about it very carefully and slowly. And maybe I'll stick with you for just this part. I just want to like think about what happens in the R loops case, right? Because that's why you came up with the idea. I'm pretty sure. So now, what happens if R of alpha loops, right? If R of alpha loops, then we're going to be running n of x forever also, right? And n of x, the way that he designed it, eventually accepts everything, right? If you run n of x long enough, it will accept any input, right? Because it has like this long delay. Like it basically like counts up to x, up to the input. And when it gets to that count, it then accepts, right? So in fact, if R of alpha loops, then what is L of m? I'll let you answer your idea. It's actually sigma star, right? And of course, this is infinite, right? This implies that m belongs to infinite, which means we have been successfully rebellious, right? The recognizer by looping said, you're going to be finite. And we're like, no, I'm going to accept everything, right? And you've managed now to accept everything, which is indeed a contradiction, right? Awesome. Totally worth a token. Questions about just this, about this idea? Yes?
So you said that we can't count up to infinity, then why would it accept?
Good. Yeah, I'm glad you asked that question, right? It's true, we can never reach infinity, right? But the input to our machine is some specific string, always, right? Let's say it was 0, 0, let's say it was a declaration of independence, okay, is the input to our machine. Okay, it's a very long string, but it's still just a string of zeros and ones, right? If you start counting all the numbers, eventually you will reach, like it'll take a long, long time, okay? Longer than the length, than the time span of the universe. But eventually you will reach the number that represents the Declaration of Independence, right? And at that point, this machine will accept, right? Like when you actually count all the way to the Declaration of Independence, you'll say, okay, if my input equals the Declaration of Independence, then I accept. And indeed, it happened to be the Declaration of Independence, so we accept, right? So for any individual string, we eventually reach it if R loops. Does that make sense? A little bit more?
It makes sense. I definitely understood everything that you were saying, but the machine itself, isn't it supposed to only accept infinitely? Like, isn't it supposed to check for only infinite?
No, 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 no. Remember, again, the definition of infinite is that the language is infinite in size. It just says that the machine accepts infinitely many strings.
Okay, now it all makes sense.
Okay, all right, very good. Yes?
Just real quick, you should say R alpha, right? At the bottom when you.
Oh, sorry. Yes, thank you, thank you, thank you, thank you, thank you, thank you. Yes, thank you. Also, definitely worth a token. If I ever make a mistake like this, please correct me. Otherwise, someone in the future will be looking at their notes and be extremely confused about what's happening. So I appreciate that. All right? Question?
Yeah, I still don't understand why we do this slow process when our eventual goal is just to accept everything.
Good, good. So in fact, to answer your question, we have to keep going. Okay? So let's actually keep going with our description. Okay? And we have handled the case for R loops, but we have to still handle the case, for example, that what if R of alpha accepts? Okay? So, and I'm just going to make a little observation, right? That if R of alpha did accept at some point, it accepted, let's say, after t steps. Okay? And that's just always true, right? Like if R of alpha accepts, it accepted at some time, right? So let's say it did it after t steps, okay? And now I want to see what should we do in this case? Yeah. Okay. So what she's suggesting is that if R of alpha ever accepts, we just immediately start to reject everything, right? We just reject. Right? And let's think about that. So I'm going to stick with you for a while. So as you explain your reasoning behind this, and we think about the analysis. So the analysis, in fact, is non-trivial, even for these cases. So that's an important point. Like, it wasn't enough for us to just handle the loop case. We actually needed to be clever about it, and thankfully he was clever in advance, right? And so now we're going to make things work. So let's think about this. So if R of alpha accepts in t steps, or maybe I should say after. Okay. Then what? What do we know? Yeah. So that means that what happened was this ran for t steps, so this ran for t steps. And let's just approximate that by saying that the for loop had t, like went t times, right? So that means n could only have possibly accepted t inputs, right? So we have that the language of M is actually less than or equal to t, okay? because after that, we just reject everything, right? So for all of the inputs that were less than t in some sense, n already accepted and we never even made it to this step of m, right? Because like we would have already halted and accepted at this point for all x's up to t, roughly, right? But for any x that is greater than t, we make it to this step and we just reject, which means that the final language is at most size t, which is finite, right? Hence, m is not an infinite, which is, again, a contradiction, right? R, by accepting, said, oh yeah, you definitely are going to accept an infinite number of strings, but we only accept it at most t things, right? So definitely good, worth a token. I imagine that there's some questions. So raise your hand if you have a question. Yes? Yeah, okay. So I said at most t just because like I was like slightly lying to you. Like for example, like just running the for loop would maybe take a little bit of steps. So like if you assume that in fact one step you actually do an entire loop of the for loop, then you're exactly right. Then it would be exactly equal to t, right? But just because we don't know, so it's just safe to say it's less than or equal to t. But I like the question. That helps like just clarify the model. If, for example, you were writing, like you had something like this on your final exam, right? And you just wrote equal to t, and you just like say, I'm assuming that like one step completes a for loop, we would give you full points. Okay, so just to be clear, it's just a super minor technicality. Yes? Mm-hmm.
If R halts, we know that N halts. We don't have to worry about N running in the background once R halts.
Good. So when I have like an if statement after a statement like running something in parallel, I'm saying like if R of alpha accepts at any time, then we just stop the whole thing. So just to be clear, yeah, that's a little like I agree that that's not normally how like how pseudocode works. But just to be clear, when I say run two things in parallel, if either of them halts, then we halt the parallel execution. Okay? And then we like come here because we know n of x will definitely never halt. Like the way that he constructed it, it's impossible that it's going to halt, right? It literally just goes on forever with an infinite for loop, right? Any other questions about this? Before, I definitely want to hear ideas for how we can finish the proof, but question?
Just say that N always halts on any given input. It just takes like the amount of time it takes is unknown.
You're absolutely right. I'm so sorry. Thank you. Thank you again for correcting me. Yes, I'm sorry. Let me rewind myself. Okay, so I didn't say the thing I just said. In fact, you're absolutely right. For any given input, n does halt in a finite amount of time, right? It's just that here we are analyzing it under the assumption that the input is like longer than whatever running time was here. So in this particular case, if R of alpha halts, but n of x is still running because like x is too big, then we just stop this whole thing and we go straight to the if statement. Thank you for correcting me. Definitely worth a token. Again, technicality, but very important. I don't want to lead you guys astray. Yes? Not a question. Sorry, just before we get to you then, any questions? Yes? Yeah. So he pointed out that just, you know, look at the code of n, right? In fact, for any given x, n does eventually halt, right? Because eventually you just reach x and you accept, right? So I had mistakenly said that n always runs forever, and that's just totally false, right? So that was it. That was the main correction. That's just like, in fact, n does always halt. It's just sometimes it takes a really long time, right? Yes. So basically, like in this class and also on your final, what I will assume, whenever you write run A and B in parallel, I assume what you will mean and what definitely I mean is that if either of them halt, then we stop the execution. Okay, and we move on with the rest of the instructions in our program. Okay? Question?
In the case that they're recognizable loops, we assume that the language of the machine is infinite just because if it's running forever in infinite time, eventually it would accept all those strings?
Yes, because n would eventually accept.
Is it kind of like I heard about this thing one time called like monkey typewriter theory. I don't know if you've heard of that. It sounds insane.
Wait,
It's
monkey?
Like monkey typewriter theory.
Yeah, okay, yes, of course. This is like a very famous philosophical experiment, right? That like, if you have a monkey, and in this case, we're modeling a monkey as a random typist, right? And you just let them type infinitely, or if you have an infinite number of monkeys typing things on a typewriter, eventually one of them is going to write out the entire like works of Shakespeare, right? Yeah.
So is it kind of like?
It's kind of like that. Yeah. It's in spirit. It's not exactly like that because there's no randomness here, but in spirit, it's saying like, it's saying the following actually to be concrete. Forget about a monkey. Imagine. Oh, wait. Did you guys grow up watching Sesame Street? Is that still a thing? No, kind of. Some people are nodding. Of course. Okay. Who's the Count guy? Oh, a Count. Yeah, the Count, right? So the Count, right, from Sesame Street, right, just loves to count, right? And he just like count. So imagine that there was a immortal vampire Count, okay? And that's all he did. He just kept counting. 1, 2, 3. But he always converted his numbers into binary, okay? And like wrote them out in binary. Then instead of the infinite monkey theorem, there is the immortal count theorem, okay? Which says that if he just keeps counting, eventually he will count to the entire works of Shakespeare. Like the number that he counts to, if you convert to binary and then convert to ASCII, will just be the entire works of Shakespeare. That's exactly the right idea. Yeah. Yes.
So that means when our program kind of counts towards that, that's when we hope and we accept.
Yes. That's when we accept. Like when you actually manage to count to that, to whatever the input is, that's when we accept. Yeah. It is pretty cool. Yes.
I kind of get this proof, but I'm not.
We're not done yet, just to be clear. Yeah.
I don't understand why we need like to run it in parallel. Can't we accomplish the same thing by running the recognizer for like X amount of steps?
Excellent. I love it. Okay, so he is suggesting an alternate proof. Okay? And I'm going to put you on pause. Let's finish this and then we'll see your alternate proof. Okay? I really like that idea, by the way. Yes? Yeah. So the looping case, right, means that we're going to run this in parallel, right? And that means for any given input, eventually our immortal count, right, will count up to that input and just accept it, right? So that means no matter what the input is, eventually our machine actually accepts it. So that means the language of the machine is actually sigma star, everything, right? And that is indeed a contradiction because that is an infinite language, right? And again, if R loops, that means that R is telling you you're only going to accept a finite number of things. Sorry, can you say it again? Well, R is looping, right? Even though R is looping, our machine doesn't loop because of this like clever idea of running these two machines in parallel. And if either of them stop, then we stop, right? So in this case, n will always eventually stop when it counts all the way to the input. And in that case, our machine just actually accepts, right? We reach this point. So even though R of alpha is looping, our actual machine is accepting. Yeah. Okay. Question? Yeah. You were going to propose the next thing? Okay. Yeah. Let's just do it. Yeah, so the only other case we have left is if R of alpha rejects. And again, this is going to be, after t steps. Although, actually, sorry, in this case, it doesn't matter. Sorry, I don't need to say it here. Okay, and then yeah, what do you want to do in that case?
I guess we actually are, so we need to make it infinite. So we simply just like accept.
Just accept, right? Just accept, all x, and this is like all remaining x, right? I guess even here I should say all remaining, just because the other ones have already been accepted. Right? So yeah, if the analysis is that if R of alpha rejects, right? Again, that means that R is telling you, oh, you're definitely finite, right? Just like the looping case. So we want to contradict that. And what you're saying is just accept everything, right? And we've already accepted, however many things because of n. We're just going to accept everything else. So then obviously L of m is sigma star, right? And that's clearly infinite. So that means the description of m is infinite, just like it was there. And that's a contradiction. And now we have reached a contradiction in every case. And that finishes the proof, right? And definitely worth a token, thank you. Right? Yes?
I have a question. So why doesn't nx just cover the reject case as well? Why can't we just say if R rejects, then do nothing, and then just let n?
Yeah, that's a great idea, right? Equivalently, like instead of this, we could have said if R of alpha accepts, just keep running. Oops. Keep running n of x. Right? That's your suggestion. Totally valid. Would have had the same result. Also worth a token. Excellent idea. Right? So yeah, that is the way that we can prove this theorem. Any remaining questions? Is that a question? No. Okay. So let's now. Oh, is that a question? Yeah. Yeah. Oh.
How is n of x different than if you just said you accept x?
It's not. That's literally the point, right? Like these are just equivalent. Like you could do either this or this.
You just replace that entire logic with just accept x.
No, because we have to handle this case, right? It's very important that if R of alpha accepts, then we've only accepted a finite number of things so far because of n, right? So this is really the key. Like we absolutely need that this is going to work out. And the only reason that works out is because n of x has only accepted a finite number of things so far, right? Yeah, yes?
Okay, for this, I was thinking like, can we just say inside a loop, like after each step of R alpha, accept the x, and like the next x is sigma star instead of building a new machine?
Sure,
Okay.
yeah. I mean, there are lots of ways of doing this, right? And this is just the way that was suggested, and so that's what we did, right? Or at least this is the way I interpreted what you said, and that's what we did, right? but yeah, there are actually other alternatives, and maybe now is a good time for us to explore an alternative, right? So you had an alternative in your mind, and let me. Okay, everyone has got this in their heads. I'm gonna now like erase part of it to suggest for us to think about an alternative way. Question? Yeah. Mm-hmm. This one? No, 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 no. You're claiming that it should only be like one? No. So remember, like n of x at that point would have accepted any x that is less than or equal to t, roughly, right? And we're analyzing the behavior of the machine on all possible inputs, right? That's really, by the way, that's why this takes a while to like sink in, right? It's like we are analyzing this machine on all possible inputs, right? And we have to like think through every possible input that could come here. Yes. Yeah. Okay. All right. Very good. Okay. So there was an alternative suggestion. So let me erase this, and let's try the alternative suggestion. Do you want to repeat your suggestion? Where here we're like interpreting x as a binary integer, right? Just to make it like you can actually even just do this, right? Just the length of x steps. Okay. And then what would you do? So if accept, or let's say like if maybe we should start by thinking about if didn't terminate. Right? So R of alpha, if you ran it for x steps, neither accepted nor rejected, right? Then what should we do? Accept. Okay. If R of alpha accepted, then what should we do? Reject. And if R of alpha rejects, then we just accept x, right? It's the same case. And that's it, right? So this is the alternative suggestion. It's really nice, right? It's more succinct, no parallel running, but a little different in analysis. So you already got your token. I actually want the rest of you to think about it. And I'll ask you guys to analyze it for me after I finish erasing. So yeah, let's try to analyze this. So if R of alpha loops, what does that mean? Let me again try to see if I can call on someone I haven't called on. Okay, I guess I've called on all of you guys, but maybe you less than others. Yeah. Well, okay. But yeah, so again, yeah, if R of alpha loops, then the recognizer is kind of telling us, hey, you should be finite, right? But what actually happens in our machine?
It runs for x steps, which is finite amount of steps, and
So like which case would we be in? Didn't terminate, right? We would always be here, right? So this is this case. So in that case, what's the language of the machine? Yep, it's sigma star, right? Because no matter what the length of x is, we're always going to be in this case. We're always going to accept x, which means our language is actually sigma star, which of course implies that m is an infinite, which is a contradiction, right? So excellent. You got us started. Worth a token. Let's continue. What is the next case here for us to consider? Yes? Okay, so if R of alpha, let's say, accepts, and again, I'm just going to like say after t steps. Okay, because it's going to take some amount of time, right, to accept. So again, that means that the recognizer is telling us, oh, you definitely accept an infinite number of strings, right? But what actually happens in this case? So that means eventually we're here, right? So what is L of m in this situation? But what would it be? It would definitely be related to t. That's true. But how? Like what strings would be in it? So let me write it this way. X in sigma star such that what? Like what must be true about the length about x for it to be accepted? The length of x is what? Okay, let's see. Equal to t. So why equal? What if it was like t over 2? Yeah, less than or equal to t, right? Yeah, right? Basically, we know that it's going to run for t steps, which means that for anything that, actually, I guess strictly less than t. It's just a minor point, but you have the right idea, right? So after t steps, we would be here and we would start rejecting everything, right? But up until t steps, so up to t minus 1, we would always be in this situation and we would be accepting, right? So you're absolutely right. We get that it's all strings of length strictly less than t, right? Which is indeed finite, right? So this means that m is not an infinite, which is a contradiction and definitely worth a token. Thank you so much. Right? Again, please, questions if you have a question or yes. X is a string.
That's nice doesn't necessarily have to go up to t, right? Like if I stop at t equals 3,
So hold on. We assume that we accept it after exactly t steps.
yeah. I mean, like I could have like 0, 1, 0, 0, 0, 1, 1, 0. So my length doesn't have to increase every step, right?
The way we wrote the code, we said we run R of alpha for the length of x steps.
Oh, okay.
Yeah. I think that was the only thing. All right. Any other questions about this case? Right? It's actually this idea is actually a little easier to analyze, I think, in some ways. I don't know. Maybe not. Everyone is different. Maybe you like the other one better, but it's all good. We have one more case remaining. Yes. Yeah, it's actually identical, right? So if R of alpha rejects, then again, we're actually just going to accept everything, right? Because both of these cases we accept. So L of m is sigma star, which means m is an infinite, which is indeed a contradiction, right? And again, we get contradictions in every case, and the proof is complete. Yes?
I'm kind of confused on why we should say, like, if it doesn't terminate, because literally when you run it infinitely, and you don't get anything.
Nope, because we only ran it for a finite number of steps. Like, we don't run it. We don't like just transfer control to R of F. We only run it for, let's say, I steps, where I is the length of our input.
And by running it for that amount of steps and it doesn't terminate, we know that it's never going to terminate?
No, we just know that it didn't manage to terminate in those I steps, right? So we like simulated it for I steps.
Yeah.
And we saw, oh, it didn't reach Q reject or Q accept, right?
Does that mean it's going to loop?
We don't know that. We don't know if it does or it doesn't, right? It just means it hasn't looped yet. But when we're doing the analysis, right, we know that if R does loop, then we always go to this case. You agree? On the other hand, if R accepts after T steps, that means for all x whose length is less than t, we would be in this case. You agree? Right? Because it only accepts after t steps, and like, so if we simulated for t minus 1 steps, we haven't yet reached q reject or q accept, right? So, right, and as a result, we only accept, because of this case, the x's whose length is smaller than t, right? So that's actually a very cool fact about this approach, right? Is that we don't actually know. Like when we're running the program, we don't know if R is going to terminate or not. We only ran it for a finite number of steps because we had this like grand plan in our minds, right? That we wanted to reach these contradictions, and that's why we did it. That's why like he came up with this idea. That's why he came up with his idea, right? Because like we knew the kind of contradiction that we wanted to get, so we designed the whole machine like with that grand plan in mind, right? Yes?
I have the same thought as you. The thing that made me realize is R doesn't depend on X. So the T is a fixed value every single time you run R. And so it doesn't change based on X, so it's just one number. And as long as every input's below that one number, then that's why it doesn't like change ever.
That's an excellent observation, right? Something we should always remember. Like whenever we have a recognizer or a decider, we just run it on our own description. That does not depend on X at all. So no matter what the input is, the running time of R of alpha, in this particular case, will be independent of the input, right? And as he said, it'll just be some fixed number t, if it does terminate. It'll be some fixed number of t, so it's a fixed number t of steps that it always takes, no matter what the input is, right? And again, that is by our design. Like we have designed our machine this way so that we could get a contradiction in every case, right? And yeah, and so you can see like there's obviously some like forethought, you know, that goes into these unrecognizability proofs. You have to really like think about it and see how you can engineer it to make it happen. You guys have been doing that today, so hopefully you feel like you have some ability to do that. Yeah, question.
Is there a way to think about this? Like, your questions is that there's like an unknown amount of different machine things. We're just like finding a certain machine that has already a set T, and that T will force a contradiction.
That's one way of thinking about this particular example. I agree with you here, right? Like here the idea was because the language was infinite, right? We knew that we would be dealing with like finite versus infinite. And then the thought was like, wait a second. If this machine does actually accept, it accepts after a certain fixed number of steps, right? And we know that in that case, we have to make things finite, right? So that's why we should probably do something so that with every step of the machine, you only add like a finite number of strings to the set of things you've accepted, right? Whereas if it loops forever, then we're going to make it accept everything, right? So like that tension, I think was, I'm psychoanalyzing this guy now. That was what was going through your mind, right? You're like, that's what I want, right? And so that's how he came up with the idea. And I think that's the same thing that was going through his mind. He was like, wait a second, I can do this in another way. Just run R for a certain number of steps, right? So the idea was the same, and that's kind of how these guys came up with these solutions, right? All right. And yeah, and like it depends very much on like the specifics of the language, right? We have to really look at it carefully. Okay, I think we are out of time. So I will go ahead and stop here. And yeah, you guys have the discussion section. Some people are going to come and talk to me about the awesome review session that you guys are organizing for each other. And then I will see you for the first part of the final on Monday.
Thanks so much. Thank you.
Yeah.